All right, my name's Eric Davis. I'm a graduate student at SUNY Oneonta, looking at ways to decontaminate watercraft after they've been exposed to zebra mussels. Get going. So the background, the zebra mussel, Dracaena polymorpha, native to the Black Caspian Azov Sea, so you're looking Eastern Europe, kind of the Russia, Ukraine region. D-shaped margin with sharp margins, concave so you can stand them up, they won't tip over, and they're usually symmetrical. That's usually used to differentiate them from the quagga mussel. Then their unique characteristic, they can attach to hard and soft substrates, and it's done by their byssal threads, which come through their muscular foot. So they put it down, they have a groove in it, and they excrete a protein. Compound comes down after it takes about 10 to 15 minutes to start solidifying. They can retract their foot and keep doing it till they get a nice big mass like that, and then they're stuck. And that's the issue. They can sit on rocks, and then what they do is they filter feed, so they're pretty nasty for the ecosystem. So here's their life cycle. Starting bottom left is the adult mussels. So they are going to be between 6 and 45 millimeters. Usually probably the average ones I've found in Otsego Lake for doing most of my research were in the 14 to 15 millimeter range. But you can get some pretty big ones. I think the New York winters kind of really dampen how well they can grow. So they do stay a little smaller up north. And then their external spawners. So what they do is they put their sperm and egg into the water, and they're going to be fertilized in the water, and then from there it can take up to 2 to 4 months, depending on water temperature, for them to go through the stages of the veligers, which are
a male and a female, or
yes.
Do they both have the same?
No, so the mussels have an individual sex. So there's a female mussel and male mussel. A female mussel, a good sized mussel, can produce up to 1 million eggs alone. So that is where you can run into a lot of problems. And then their veliger stage, starting in the upper left, the trochophore is really small. The straight hinge is typically referred to as a 3-day-old veliger. It looks like a D, they call it D shape. Then they just keep getting bigger till they get to the pediveliger in the upper right. That's where they actually have a little siphon. You can see it under the microscope. Now once they get to that stage, they're getting kind of too big and they can't float anymore in the water, and they try to find something to settle on. That's when they metamorphosize, turn into really small mussels, and then it takes a couple months for them to become sexually mature so they can start spawning. You can have them reproducing in the same year that they were fertilized as veligers. So the study goals and objectives. Everyone's already heard the hot water, high pressure decontamination station works good. The emphasis that my study is find something other than that can work, because they can cost a lot of money to build, cost a lot of money to run. And there's been a couple spots out west where they get boats, they wash them, they give you a certificate that says my boat was washed. That boat shows up at another boat launch a couple miles away, and it has live mussels in the boat, so it's still not a foolproof method. So it's find ways to decontaminate your boat that you could suggest to the public. So it needs to be something pretty straightforward, simple, a chemical that's not going to cause you problems if you're doing chemicals. They just want it so that you can, if someone doesn't want to sit and wait for a boat wash, what can you do at home? So the first objective was to test a bunch of chemicals that you can find around the house, and see how they are toxic to adult mussels and to veliger the larval stage. Second was to determine if you could use a commercial car wash, which typically does not have heated water in it, to remove adult mussels or attached mussels, because they might not be adults yet, from a watercraft if they were to show up at your boat launch. And the third was determine if you could flush the live well or the bilge of your boat to get veligers out of there, under the concept that trailered watercraft is typically described as what the issue is and how the zebra mussels are spreading. So the leftover water in your boat, once it's on a trailer, can have veligers in it. So under that, you're saying that once you get to a new boat and you turn your bilge pump on, you're pumping veligers into the lake. So this is saying, can I stop at home and rinse them out completely out of my boat before I go to the next lake? So the first thing I did last fall, or I guess 2 falls ago, fall of 2014, did my chemical test to adult mussels. So I collect them in Otsego Lake. I do all my research out of SUNY Oneonta's biological field station. It's in Cooperstown. It's right on Otsego Lake. Collected mussels, put them into mesh bags, put them in the aquarium in the greenhouse, and it has fresh water from the lake getting pumped into it, so it's replacing the water nonstop so it stays oxygenated, because you need to keep fresh water on the mussels to keep their stress level down. Otherwise you start having mortalities from handling them. And then right before I would put them in the chemical tanks, I would check all the bags, look for any dead mussels, because I was scraping them off with paint scrapers. So sometimes you would get a mussel that had chips in the shell that you didn't catch the first time. That would obviously skew your results if they don't have a full shell to kind of protect themselves from your chemicals. So in the end, I would always have 10 mussels in every bag. I'd have 10 bags for every tank, and I had 30 tanks, or 15 tanks, so 3 replicates of 5 chemical concentrations. Put them on the dowels in the tanks. Once every tank had mussels, you take the first one out, it's time 0. It's essentially a control saying the mussels were in there for less than 5 minutes. After that, every exposure period, which was 1 hour, 2 hours, 4 hours, all the way out over 4 days, take 1 bag of mussels from every tank and walk them out and put them in the flow-through aquarium outside. And that's because certain chemicals, especially ones that contain potassium, have been shown to be almost like an anesthesia, where it will knock the mussel out, it'll look dead, and then if you put it in fresh water for a couple days, it no longer looks dead, it's nice and alive. Like a zombie. So I'd let them sit for at least two full days, sometimes 3 days, depending on my class schedule, before I'd go through and check them for mortality. So for that, I would put them on a paper towel, because then I could dry them off to handle them, because I was going to end up measuring them. They're considered dead if the shell was wide open, just like this picture. It's fairly easy to find if they were dead or not, like that. If they had a slight gape in their shell, I would poke there with a pointer, and if they would close, they're alive. If they would stay open, I would consider them to be dead. Then I measured the shells, and then entered into Excel along with whether it was a dead mussel or a live mussel, because then you could do statistics looking at dead mussels, live mussels, and how long they were. The chemicals I tested, first one was distilled white vinegar, which is 5% acetic acid. It was Walmart brand. The concentration, so 0, 25, 50, 75, 100% vinegar, so that's out of the jug. So a 50% vinegar would be half water that I took out of the tap and half vinegar I poured out of the bottle. And then potassium chloride is a chemical that's been suggested for use in fish hatcheries, and it's suggested to be a little less corrosive than sodium chloride. And then sodium chloride at the lab grade level, iodized table salt because it's a lot cheaper, and water softener salt because it's even cheaper yet. And 30,000 milligrams per liter comes to roughly seawater when you look at the sodium chloride. And knowing that it's a freshwater organism, you know, in salt water it's going to die at some point, so it's looking to see how fast that would happen. So distilled white vinegar is by far the most deadly chemical to adult mussels that I've found. Looking at with just vinegar straight out of the jug, 1 hour killed every mussel. You can dilute it out. 50% water was 2 hours, 50% vinegar, 50% water took 2 hours. And then 25%, so 1 part vinegar, 3 parts water, took 4 hours to kill all the adult mussels. What's good is you're not as likely to find adult mussels washing around in someone's boat unless you usually find them around gear that's going to be on the bottom, so your anchors, ropes, things like that. So next would be potassium chloride. So 30,000 parts per million or milligrams per liter took 6 hours to cause 100% mortality. And the 10,000 took 12 hours. And then on to sodium chloride, the lab grade, took 24 hours to be completely deadly. And then 10,000 took the full 4 days. And the 10,000 is a concentration they recommend for some fish hatchery use because it doesn't cause any harm to a lot of the fish hatchery fish, but it will cause mortality to the veligers, which I'll get to later. So iodized table salt, 24 hours, so it worked just as good as the high-grade salt, which is nice when you do a cost comparison, which is towards the end of my presentation. 10,000 was at 3 days instead of 4 days, a little faster. I don't know if the iodine aided in that or if it's just that group of mussels. I know on the high-grade sodium was close at 72 hours. Oh, wrong way. And then lastly, water softener salt took 48 hours. I had one stubborn mussel that did not die at 24 hours.
Like soft water.
So I consider it most likely to be a product of water softener salt having a higher level of impurities in it, because it doesn't need to be as pure if you're using it just to soften your water. Then on to the veligers. If anyone hasn't seen a veliger before, this is what they look like when you use a cross-polarized microscope. It causes the shells to be highlighted so they have the black cross on them. Otherwise, without the filter, they just look like little black blobs and you don't know what you're looking at. So I would collect water, veligers out of the lake water, put them into some bottles and bring them back to the lab. I'd concentrate it down to try to get a lot of veligers and a little bit of water, so it's easier to work with in the lab instead of having 5 veligers per liter. I wanted it a lot higher. Count them using the cross-polarized light, so I'd get an average per milliliter, so that way when I was putting them into the chemical solutions I had a rough estimate how many should be there. So I'd put 1 milliliter into 24 milliliters of a chemical solution, and then after the exposure period was over, I would filter them with my veliger holding devices, which are just centrifuge tubes that are cut and put filters in and rigged up to hold them. I wanted something that would hold the veligers in there so I could put them into fresh water and have the water circulate through the bottoms. There's a hole cut in the bottom of those with a filter. I'd rinse them with lake water briefly, and then I would run to the microscope and count how many were alive versus how many were dead, and then put them back in the aquariums like that and check them every day I'd try to do 3 days. Sometimes I had high mortality level in my controls, so I can only do 2 days. So the chemicals, real similar chemical list: distilled vinegar, potassium chloride, sodium chloride, and iodized table salt. The concentrations are a little lower other than on the vinegar, because these are concentrations that had been recommended for either use on quagga mussel veligers in the western U.S. or in some of the early zebra mussel research in the early 90s that hadn't really been redone. And then exposure periods were also based off what the previous studies suggested. In the results, vinegar, no matter what it was, worked, similar to in the adults. Potassium chloride worked at all 3 concentrations at all the times. And it's most likely because the veligers can't hide as good. Like an adult mussel can close its shell when it detects a chemical. The veligers don't really have that capability. They have a little shell. I might have a picture of it coming up. But it's usually not as good, so they can't withstand the chemical. Then sodium chloride worked at 18 hours at 10,000, which is shorter than was recommended before, which is good. Then iodized table salt, only the higher concentration worked at the same time as the lab grade sodium chloride. A direct comparison that we did between sodium chloride at the lab grade version versus the iodized table salt, there was no difference based on the chemical. So that you could infer that means that it works just as good. And it says iodized table salt instead of salt, which is nice when you do the price comparison. Potassium chloride was significantly more effective than sodium chloride when at the same concentration, which means it's working faster. So the pressure washer to remove attached mussels. So we sacrificed a canoe and made it into a bunch of little fouling plates and hung them in the lake in August of 2014. Then in October of 2015, I went out and took them all off the racks. I would isolate a cluster of mussels that had colonized the rack, take pictures with rulers on it so I could go back and do density per meter squared or whatever unit I wanted to do. And then I would blast them with our pressure washer, and I just wouldn't turn the heater on because that does have a heater in it, so you can heat the water. And the pressure on our washer was a little over 1,100 psi. I'm looking at I think it was the Lake Champlain Basin pamphlets. Most of the boat washes they recommend in their area are between 1,000 and 1,500, so this is very comparable to a car wash where you go and put your quarters in and do all that. So looking at the results, this is time to remove versus the number of mussels in a cluster. And there really was not a pattern that went with it. And that's why there's no linear correlation. So number of mussels increasing did not mean time to remove them increased, but it didn't decrease. It was just kind of flat. Not really sure why you would think more mussels would take longer, but it could be that the size of the mussels was pretty small. And when you compared it as density of mussels, it was pretty much the same. And here's why I think there could have been that. So we had 2 distinct age classes. This is shell length versus frequency. This is very common in the fish world when you have different age classes of fish. So it's showing that there are some mussels attached to the plates right away because they can move, even though they are, once they're attached to something, they can unattach and kind of move around a little bit. And then the smaller mussels are from the same year. What's good is in New York, you're very unlikely to see boats with this many mussels on them or big mussels on them because we have winter time and not a lot of people leave their boats in the lake when it freezes. So you could use a car wash to remove all the mussels if you did have a boat show up at your launch with mussels on it, because if they're from New York, they're likely going to be really small mussels that don't take that long to remove. You can run into the issue with the bigger mussels. I had one panel that took like 8 minutes, So if you extrapolate that to a 16-foot boat worth of that, you're looking at, it was like 7 hours. But there are some that took less than a minute, so you're looking at a lot shorter time. So just hopefully you don't have like one of those pictures where it's like just nothing but mussels. That would not be something you'd want to try to wash. It'd cost you a lot of quarters. So to flush the live well, this is a picture of what I was working with at first. So it's a lot of sand, and there's one zebra mussel villager kind of towards the middle of that picture. So I filled the live well of a boat with it was 6 gallons, but since a lot of science likes to go with metric, I rounded it to 22 liters. And then I would put villagers in the water and let it sit for a couple minutes so they would kind of disperse throughout the whole live well. Then I would pull the plug and let the whole thing drain. So just like you would have someone leaving a boat launch, now they're required to drain their live well. So then I would flush it with, I have a picture of my sprayer in a little bit. Is the equivalent of a garden hose. It's converted, it has the nozzle where you can change it to like the 7 different sprays like you can buy at any hardware store. And I'd flush it for 7 minutes. For the first 5 minutes, every 30 seconds I would change a filter underneath the drain. I had a funnel coming out, and then I'd change the filter at the end of the drain line every 30 seconds. And then after 5 minutes, I would do just 2 minutes of washing, let it drain for 3 minutes, so a total of 10 minutes, and that would be my last filter. And I took filters in and back flushed them and concentrated them back down, and I ended up preserving them to save time instead of trying to look at them right away, because I was running out of summer when I started doing this. And since the emphasis is did they get out, needing to know whether they were alive or not was not a concern, so preserving them really didn't make a difference. And then I spent the winter and some of this spring looking through the samples and counting how many villagers there were for every time interval. 5 minutes was not enough time to get all of them out. I had an average of 4.8 villagers in the last sample bit. So that means after 5 minutes of washing, there is on average at least about 5 villagers still in the live well. A good positive note to take away could be that in the first 2.5 minutes of flushing, on average 90% of the villagers that I counted were from the first 2.5 minutes. So this kind of shows the graph. The first 30 seconds had the highest, as you would expect. That's the first good wave of water coming out of the live well. And then as time goes on, it does decrease. We did the correlation coefficient on that was -0.6. That means over time, it's getting significantly less and less villagers.
Just a clarification, Eric, was this water at ambient temperature?
Yes. It was water coming out of the lake. So I'd fill it up with our hose coming right out of the lake, put it in there. Yeah, everything, nothing heated, nothing special done with the water.
So Eric, when you say 2.5 minutes of flushing, that's with the plug open and you're hosing it
Yes.
down? It's
Yep.
not filling it and waiting 5 minutes
Nope.
and letting it out?
No,
Okay.
it's with the plug out and it's draining as you're putting the water in. So some things to consider when you're thinking about it. Chemical treatments, they are limited. Trying to put chemicals all over the outside of your boat, very unlikely. You're not going to make a pond of potassium chloride water and expect someone to launch their boat in it. And then you have to have it sit there for 6 hours. So not likely. But gear immersion, so your ropes, your lines, chains, anything like that, you can put like into a 5-gallon bucket of chemical solution, is possible. Things like the live well or the bilge where you can plug it and stop the water and allow it to sit for the required time is something you could do. First question I always get is, well, what do you do with it when you're done? You kind of got 2 options. You can either, depending what it is, might be able to reuse it. So something like distilled vinegar, you're relying mostly on the pH is what's causing the mortality to the mussels. You're not going to lose the pH value that rapidly with that, so there's the potential to catch it and reuse it, because everything that's in it is going to die. When you're looking at it, you just need the pH on the distilled vinegar at 25% is down at 3.6, so it's extremely acidic. You could run into issues with some of your equipment not being equipped to handle pHs like that. And that's where you might have to go with something like the potassium chloride or sodium chloride, and you have to deal with long exposure times. You could also invest in one of the capture pads that they use at some of the wash stations. So then you're capturing all of the chemical solution as it's coming out of a boat. And then you can dispose of it properly or reuse it. And the pads go for anywhere between $3,500 to $5,000 for the pad. And you probably need to buy a pump to pump the water somewhere out of the pad. Converting it to usable terms, this is another one. Everyone goes, well, how much is 30,000 milligrams per liter? For salt, it converts to 0.42 cups per gallon. So you could round that to a half a cup per gallon and have it a little heavy on the salt side. And then you go to 10,000, you'd go a third of that, so you're at a sixth of a cup for a 10,000 part per million concentration. One drawback, hardness and conductivity of the water can influence the effectiveness of potassium chloride and sodium chloride. Super conductive water was found to decrease the efficiency of them, because generally there's enough ions in the water that the mussels when they take in the potassium ions, they're able to quickly swap them out for the other ions that are in the water. So if your lake is super conductive, you might have an issue using sodium chloride or potassium chloride as a decontamination method. And the second one is zebra mussels can have a greater salt tolerance based on where they're living. So if they're living in a more salty environment, close in a brackish area, they can generally tolerate more salt, whereas Otsego Lake doesn't have a lot of salt, so it didn't take a lot of salt to cause mortality. Some other things to consider when you look at the car wash, the ability to decontaminate an entire boat is questionable. A 16-foot boat could exceed 7 hours of washing if they are bigger mussels that are heavily colonized on the watercraft. And then live well flushing, only 1 out of 30 replicates had 0 veligers after 5 minutes. But I had 5 of them, I think, that had greater than 10 veligers after 5 minutes. But you do get greater than 90, and I think if you move it to 3 minutes, it's greater than 95% of all the veligers that came out were in the first 3 minutes. So that could be if you really can't do anything else, at least put your garden hose in your live well for 3 minutes, and you're going to do something, which is a lot better than just leaving it. Then the cost. Potassium chloride, that's lab grade or reagent grade potassium chloride, we bought it for $42 per kilogram, which is pretty expensive. Comes out to $5.83 per gallon of treatment. The sodium chloride, that's the lab grade, is a little cheaper, and it ends up being $5.42 per gallon. Of the high concentration, if you do use the lower concentrations, it'll cost less. But iodized table salt, $1.17 per kilogram, you're looking at 17 cents per gallon, when it works just as good as what would have cost you $5 per gallon. So you're able to stretch your money farther if you use that. Distilled white vinegar, we bought for $2.50 a gallon at Walmart, and it converts to 63 cents per gallon when you dilute it out to a 25% solution. And then here's the asterisk one. Potassium chloride water softener salt. So if you have a water softener system and you might have heart problems, anything like that, they recommend you use potassium chloride because it will replace the sodium instead of using sodium in your water. You can get it at Lowe's for per kilogram, so it's got to be about $30 per 40-pound bag. You can get it. I found it at Lowe's in Binghamton pretty cheap a few weeks ago. That can convert out to 23 cents per gallon of the higher concentration, and potassium chloride worked better than sodium chloride, a shorter time. The issue is I didn't test it because I couldn't find it in the Oneonta area when I was looking for it. So to test that first would be good, but if you could get it for 23 cents a gallon to treat water, that'd be much nicer than $5 a gallon. Commercial car wash, depends on how many quarters you have in your car, can cost $3 for 4 minutes or something. You could buy a gas motored pressure washer in the $1,000 ballpark. And that's not going to heat your water, that's just going to put out high pressure water. So this is the sprayer I was using for the live well flushing. This was the DEC, it's all DEC property, they just gave it to me, said hey, test this out, we already paid for it, so it saved me a lot of money. Cart, $60, the pump that's in the tank, $60 to $100 depending on how big of a pump you want, I guess. Tank is $50. Hose and nozzles you can probably get less than 50, and then it runs off a 12-volt battery, like a deep cycle marine battery, so you can use it all day. Costs about $100. You're looking at $300 to make one of these little cart sprayers you can wheel around with you, and to flush out live wells and bilges. So acknowledgements, all the funding comes through the Environmental Protection Fund, administered by DEC. And thanks to Brittany and Catherine for inviting me to give my presentation today.